I'd like to now do a bit more with the Quake model. So it turns out the Quake model is very useful when we try to understand the effects of an intervention. Just as a review, this is the Quake model. So my y is just some intercept plus some, this is an autoregressive term in y. It's not in terms of eta, it's in terms of y. There's some x effect, and then I've got some errors, which we'll call eta. Eta we're going to assume is an ARMA process, and what's really important about this is that it have mean zero. Let's say that there are two periods. So officially something happens at time big T. All of the time prior to big T, I'm going to call the pre-period, and then everything that happens after that is the post-period. We're going to consider two possibilities for this xt variable. The two possibilities are sometimes called the pulse and the step. What's the difference? Well, pulse is where something happens exactly at time t, like we get a giant boost in our advertising spend for just time period t, and then it goes back to normal. Other than at time t, there is no change, but something big happened during time period big T. Step, on the other hand, is where there's a permanent change. Step means that y sub t is equal to 1 for all values of t at greater than or equal to big T prior to that. So in the pre-period, it's a 0. So this could be something like we had our old positioning, and then all of a sudden at time t, we change the positioning of our brand, and we continue to use the new positioning to this day, as opposed to a temporary pulse effect. We're going to consider two main cases. So one case I think is conceptually a little simpler, and we're going to start with that one. And that is where we assume this phi is exactly 1. If phi is exactly 1, we can write this equation up here as well. Yt is just c plus whatever my sales were last period plus the effect of x, and then we got our errors. Because I fixed this coefficient at 1, I could move it to the other side. So let's do that. If I move this yt over to the other side, I have yt minus 1. But that's just the difference in y. It's like we've differenced our y's, and then what will happen is this difference is going to be some drift constant plus whether or not we're in the pre or post period. So in the pre-period, this term goes to 0, so this whole thing goes to 0. In the post period, this is 1, so the differences are c plus beta. Now, there's also some errors, and these errors have mean 0. This could be a little bit higher, so the difference could be a little bit higher than c plus beta, or a little bit lower than that, but on the average, the difference is going to be c plus beta x. But let's think about what this equation looks like. So during the pre-period, the beta goes away, and if you were to write out this equation, I'm not going to do it right now, you'd find that yt is just some initial value plus c times t, and then you've got a bunch of errors. These errors get added up, but a bunch of errors that have mean 0. So this looks kind of like a regression model. We start out at some, when t is 0, this is the y value, and then for every additional step in time, the line goes up by c. So what I'd like you to note is this is just a line with slope c. Now what happens after big T? So we can think about calling this t plus h, where h is greater than or equal to 0. think of h as how many periods has it been since big T happened. So then we can think about what the line looks like. Well, for the pulse model, so the pulse model is where you get a shot of advertising this period and then it goes back down. You can work out that this is simply going to be yt plus ct plus beta plus some errors. Maybe it would help to actually work through where I'm getting these equations. So let's go do this. So remember what I said, yt is just c plus, well, yt minus 1 plus beta times xt, and then we have some errors. Let's ignore the errors for now. So you can think about, what is y1? Well, y1 is just c plus y naught, and then if t is less than t, this would go to 0, so plus beta times. Then y2 would be c plus, well, y1, but this is c plus y naught, where I take this is 0. So let's just go drop all of that in right here. And we recognize this as 2c plus y naught. Well, let's go do time period 3. So this would be c plus y2, but this is c plus 2c plus y naught, where I'm just dropping in what I have here and putting it there. So this is 3c plus y naught. And so what I'd like to point out is that for general t, yt is going to be, then we see the pattern, y naught plus t times c, and that's exactly what I had. If you want to see what happens in period big T, so let's just say that t is equal to big T, then y sub big T should be c plus y big T minus 1 plus, well, beta times x big T. Well, this is going to equal 1 now. So let's go fill some stuff in. This is going to be c. What is this term right here? Well, this is going to be what I had up here. So y naught plus t minus 1 times c. And then this is going to be plus beta. And then we can collect some terms. So I have y naught plus beta. You can think about that as a new intercept if you like. And then this and this works out to be t times c. So it's like the whole line is going to shift up. If you have, what is yt plus 1? Well, that's going to be c plus y, y sub t, and then beta times x. No, let me emphasize that was capital T, so this is big T plus 1. In the case of pulse, this is 0, so that whole term goes away. This will be y plus, well, whatever I had up here, y naught plus beta plus tc. So I have an intercept of y naught plus beta plus, okay, now I have t plus 1 times c. So if we wanted to sketch this thing out, it would look something like this. Here's t. This is my y variable. This would be y naught. And I'd have a line with slope c. So for a change of 1 in this direction, it goes up by c. And then what happens is we hit time period big T. And at big T, this line is going to shift up by beta, but the slope doesn't change, and it will carry on. So that is what this, this graph looks like. What about for the step function? Well, for the step function, remember these x's will stay at 1 for all values greater than t. In that case, what we end up with is an equation that looks like this. So we have y0 plus ct, and then however many periods I go beyond big T, plus 1, that's how many times the slope changes by beta. So what we can think about is the slope after big T is going to be c plus beta. So I've written a little function for us, and this function will allow us to pass values of beta phi. This drift is the c term. You can give it a y0 if you want. You can tell it if you want pulse or not. So pulse means I get a shot at time t. Not pulse means it's a step function. And then you can specify where you want the big T to be and where the end of the series is. So let's just go take a look at a couple of these. Maybe I'll start with this one. This graph was generated with the following call. My y0 was set to be 0. The drift coefficient is 1. And so we see the slope here is 1. Then I set the beta to be minus 2. So at the value 20, you can see the whole line shifts down by 2. I've set my phi to be 1 because that's what we're doing here. So that's what the pulse model set to true. Now, what about if we don't have pulse equal to true? So I have the same parameters. Drift is 1, beta is minus 2. Remember, drift is the slope of the line in the pre-period. Then my slope in the post-period is going to be the sum of these two. So 1 minus 2 is minus 1. And so the line reverts to having a slope of minus 1 in the post-period. So we can think of this as the linear spline model that we were fitting back in machine learning, and we've tried it a couple times in this class. Let's go look at a couple more examples. So here I've set the drift constant to be minus 1. So we see a slope of minus 1 in the pre-period. Beta is equal to 1. So the slope in the post-period is the sum of these two, which is 0. And so what we see is something that very much looks like a hockey stick, where we have slope minus 1 here, and then it flattens out to 0. Well, let's do just the opposite. So having a drift constant of 0 means give me a slope of 0 here. Then I set beta to be 3, and so we should have a slope of 3, more technically 0 plus 3 in the post-period, and that's exactly what we see. So those just give us a couple functions that can be used to capture the effect of some intervention. Now let's cover the other case, which is a bit more complicated. In this case, the absolute value of phi is going to be less than 1. Let's go remind ourselves what this function was. So now we don't count all of previous period sales, but just a fraction of it. So the question is, what does this look like? Well, you can do the type of algebra that I did on the other case and work out what's going to happen in the pre-period. So I guess we could go do this. Yt, remember, is my drift constant c plus, well, let's see, I have phi times yt minus 1 plus beta times xt, plus I've got some errors. So let's go to the pre-period. So the pre-period gives us, we have a t less than big T, and we know that xt is equal to 0 in the pre-period. So that's going to make our life a little bit easier. Well, let's start with the simplest case, y1. So y1 would be c plus phi times my starting y0 And then you can think of plus 0 plus some errors. So eta 1, if you want to write that out. Well, let's go do y2. So y2 would be c plus phi times y1, and then I got some errors. All right, well, let's go fill in what this is. So this is going to be c plus phi times c plus phi y naught plus errors, just by ERR. So I think we can start to see what's happening here. We have c plus phi times c plus, I got phi squared times y naught plus a bunch of errors. Let's do one more term, and maybe we don't need to do another term, but just to make sure everybody has this. So this is going to be c plus phi, and this is going to be y2 plus a bunch of errors. And we can go drop in what we had before, so this is going to be c plus phi times this whole thing right here. Well, this whole thing right here, that's what y2 is. So c plus phi c plus phi squared y naught plus errors plus errors. All right, so the errors are going to get combined because they all mean 0. So let's work out what we have here. We have c plus phi times c, then we have a phi squared times c, and then we have a phi cubed times y naught, and then we got a bunch of errors that get combined together. So I think we can almost see the pattern here. So yt, assuming we're still in the pre-period, is going to be, I can pull a c out, times the sum, I equals 0 to t minus 1. This is going to be phi to the I. Then I have phi cubed times y naught plus some errors. All right, so what I see is this is a geometric series, and this is going to approach the value c over 1 minus phi pretty quickly, as long as phi isn't very large. If phi is modest, this is going to approach this limit fairly quickly. You know, again, if this is, oh, I just noticed this should be a t, so let me put a t in there. This will go to 0 because phi raised to a big power, phi is less than 1. This is going to go to 0, therefore this whole thing will go to 0. Now these errors, I just want you to notice that the expected value of the errors equals 0. So on the average, this yt is going to approach this constant. So the function is going to look something like this. Here's t, here's yt, this is my y naught value, and there's going to be an asymptote at c over 1 minus phi that we approach with that rate. So that's going to tell us how fast we get up to that asymptote. You can work it out for both the pulse and the step function. And what you're going to see is that what happens with the pulse function is going to be fairly similar to what we had before. We will get a pulse in one period, and then this thing goes back to 0, and we end up with something going to c over 1 minus phi again. Whereas if we do a step function, we're going to get a new limit. So the asymptote is going to be at c plus beta over 1 minus phi. Let's go look at a few examples of this using my function in R. So we're going to start out where the pulse is true. So we get something happens. There's been a crisis. So maybe these are our sales. The crisis happens, and then our sales come back up, creep back up to normal, and they approach where they were before. So this is going to be generated by having my drift constant of 0. That's going to determine the slope in the pre-period. So we can kind of see that here, the pre-period. Then what's going to happen is this beta 2 tells me the amount that the sales went down after the shock, and then this phi determines how quickly it comes back up. And off to the right, actually, I've changed phi down below to be 0.8, and I also changed beta to be positive 2, so here something good happened. Our sales went way up, but it was just a temporary thing. It's like a sugar high. And because my phi is 0.8 versus 0.5, you're going to see it takes a little bit longer for this thing to get back to where we were. But since it was just a pulse, it's going to go back to where we started. Let's go see what's going to happen if I have a step function. So the functions on the right are where we make a change to advertising at time period 20, or maybe our competitor does something to us at time period 20. Anyway, what happens is our sales go from here and then they gradually go down to this new level. Or down here, I changed two things. We made beta positive, so it has a good effect, but it's going to take a little bit longer to get there since I increased the value of phi. So this is a geometric series. These are all geometric series that describe how this function is going to reach the limit. Let's try a few more values, and you can get a wide variety of functions by playing with these two values. So what I've done in these functions is to now set my drift to 1. So what that means is the function is actually going to have a slope at the beginning, an approach, c over 1 minus phi. So that's this green line. So you can see that we, with the pulse on, we go up until we hit close to c over 1 minus phi. Then our sales drop by 2, and then they go back up and they approach it again. If I change a couple things, so let's slow down this rate. So I'm going to change one thing. And so what you'll see is it now takes longer to get up. We lose 2, and then it creeps back up back to where it was before. So those are both examples of pulse functions. Let's try some without pulse, so in other words, step functions. Here things go up, something happens, the competitor does something to us, and our sales fall to some new level. So that happens at c plus beta over 1 minus phi, which would be minus 2 in this case. And if you slow things down by changing phi, you'll see it approaches these limits more slowly. So the point I'm trying to make with all this is you can get a wide variety of functions by playing with this Quake function. Let's go take a look at an example. So we did this example back when we talked about regression models in week 2. Let's jump over to R and do it live. Here's a situation where we sell some cereal and something bad happened in week 88. So in week 88, the competitor launched a brand that was targeted right at ours. And so the question is, what happened to our sales because of the competitor? I've created a data set where I've got a post variable. So post is going to be my x. I'm also going to set myself up to use a linear spline the way we did back in machine learning. This T88 post variable takes the value 0 up until period 88. And at period 88, it's going to tell me, it's like h, how far has it been since the competitor, how long has it been since the competitor launched the competing brand? So in period 88, this T88 post is going to be 0. In 89, well, it's been 1 month since the competitor did launch the brand. Period 90, it's going to be 2 months, and so forth. Let's go look at what this plot shows. This does not look good. You know, our sales were climbing steadily, looks almost like a perfect linear trend. And then once the competitor hit us in '88 with the competing brand, our sales have decreased. It looks like linearly. So when I look at this function, it looks a lot like this thing. So we're probably going to want to try something with differencing. So I'm going to try a couple things. First, I took this from another textbook, the Montgomery textbook. I'd recommend analyzing these data sets with some simple methods as well as the fancy methods. The reason for this, I think it's very easy to get confused with the fancy methods. I'm the first person to get confused by the fancy methods. So that's why I'm really emphasizing go do the basic models that maybe don't treat your errors right, but get you in the ballpark. So the first thing I'm going to do is we're just going to compute differences. Remember, if we go back to this model, if we take first differences should be constant. And that ought to make a certain amount of sense to you. If the first differences are constant, what that means is, here's t, here's yt. So the differences all have to be some constant, which is c. So every period we go up by c. So if the first differences are constant, that would tell us that we've got a line, a linear trend, and I think that's going to fit pretty well here. So let's go do, this is very similar to the, what did we call this? The drift method back in chapter 1, where I just find a bunch of my first differences and average them. And so we find that the average first difference is about 1161. So I might just go write that down over here. So we'll call this the mean of the difference in the pre-period versus the post-period, and we see a mean difference of 1161. If it helps, go back to the auto plot. We could think of this as the slope. So for a run of 1, we expect our sales to go up by 1161. Well, now let's do the same thing for the post-period. We'll take the mean of the differences, and what we see is that the mean of the differences is negative, so minus 2346. So I just wrote that here, and we can think about that's the slope in this region. Now if I take the difference, that's going to tell me how much did the slope change. So minus 3508. So let's just call that the change in slope. So we've gone from a positive 1161 to a negative 2346. So in other words, the slope went down by 3508. I'm going to go make a plot of this. It's hard to really see what's happening with the differences because there's a lot of noise here. Let's go add time of the intervention, and then I'll add the two means. The mean difference was this positive 1161, then after period 88, it dropped to be minus 2346, which are the numbers that we computed up here with simple differences. These numbers should be in the ballpark. Let's go try another approach. I'm going to go do a linear spline using OLS, as we did back in week 2, as we did back in machine learning. And so let's go take a look at what we found. So what we see is the slope in the pre-period is 1128. So I'm going to write that over here as the linear spline. And it's in the ballpark. I mean, those two numbers, both 1100 and something, but they're a little bit off. This number, so go back to what we went over in week 2. This is the change in the slope. So minus 3839. So I just wrote that here. That's the change in the slope. And if you want to know what the slope is in the right region of the graph, we could actually go compute it. So if we take the sum of those two, we get minus 27. So the numbers are in the ballpark. Not quite the same, but pretty similar. and we could go look at a plot of this. So this line would have slope 11.28. This line would have slope minus 27.10, which is very similar to the difference approach. Let's now try to fit a model with the correct errors. The first model that I want to try is a moving average. So that's what the autocorrelation function is suggesting. And we'll go see what happens. So I'm going to do this on the differenced sales data, and I'm going to include the post variable as an x. So the way to think about what's happening here is that's going to be my beta. So how does the differences change? And really what I'm doing is I'm just estimating the model for simple means, but with fancier errors. Let's go look at our residuals. What we see with the residuals is they look great. There's no problems with the ACF. P-value here is giant, so this model with a moving average really seems to have nailed it. And my time plot also looks really good. The errors are normal. So everything's looking really good. Let's go interpret this model. So this intercept is going to be the kind of a better estimate of the difference in the pre-period. So let's call that 1193. So y bar with differences. So it's the average differences with an MA1 model. And you'll see that's fairly similar to what we had before. This x-reg coefficient says, how will this mean change when I go to the post period? The mean of the differences shifts down by 3570. So minus 3570. The sum of those two, let's go compute that sum, would actually tell us the mean in the post period. So minus 2378. So this is the mean of the differences in the pre-period, the mean of the differences in the post-period. This is how those differences change. We could also do the linear spline model using a moving average. So let's go do that. How would we do that? Well, I'm going to include both t and my t88 post variable as predictors. We will give it one moving average term, and let's see what we get. First off, let's go look at our residuals. Not bad. There's a couple ACF values that are borderline significant. This value, the overall p-value is nowhere near being significant. So I'm inclined to say this is a pretty good model. Let's go interpret it. The thing to note about this is our slope will be the slope in the pre-period. So 1128. So this is the spline with the moving average errors. And notice we got exactly what we had before. So that doesn't surprise me. OLS gives us unbiased estimates, it's just that the standard errors are wrong. So it doesn't surprise me that those two are the same. Our change in slopes is a little bit different. So minus 3820, if we round correctly. So minus 3820 is a little bit different than what I had before. But remember, these are in thousands, so it's not that big of a difference. And if I go find the sum, this would be the slope in the post period, so minus 2692. We can go make a plot of this, and what we see is something kind of interesting. We get a wiggly line. These are one period ahead forecasts. And remember, we're incorporating the moving average errors in those forecasts. And so that's why it wiggles a little bit. If it helps, actually, let's go back. I'm going to take us back to the previous model. We're going to get the same wiggles. That's really hard to see, but this is due to the moving average errors. It's probably a good idea. So let's go back to this previous model and just state estimated regression equation. So the estimated regression equation would be something like this. YT is equal to 1193 that's that number, minus 3570, so minus 3570 times x. And then remember, we have some eta errors, where these eta errors equal epsilon t plus, okay, our moving average term, so minus 0.7179 times epsilon t minus 1. And these epsilon t's are distributed normally with mean 0 and variance, big variance. And that's because these numbers are so huge. So it's 86 million something or other, 87 million. And that would be our estimated model. You could do this exact same thing with our linear spline model. But I guess what I'd like to emphasize again is start simple. So I think these two models are real easy to understand. This one really isn't even a model. And this tells you what's in the ballpark, realizing that the standard errors for these things are going to be wrong. Then go fit your fancy model using ARIMA, and you'll get something that's a refined estimate, and I would go with one of these estimates rather than these, but this gets us in the ballpark, so I can't emphasize that enough. That's it for our coverage of intervention analysis. Have a good day.